So, schönen guten Abend. Good evening. Welcome to Nachts auf der Sternwarte. Today we have a talk by Francisco Aros about the wonders of stellar interactions in globular clusters. Francisco started his PhD in Heidelberg, then came to Vienna in 2019, if I remember correctly, together with our current institute head, Glenn van der Veen. After finishing his PhD, he went to the US, to Indiana University for a postdoc. And recently, he came back for another postdoc in Vienna, because Vienna is nice. And yeah, glad to have him back. And we're looking forward to his talk tonight.
Thank you. Okay. Yes, then. Huh? Okay, I guess that you can hear me. So thank you for coming. So today I will talk about the interesting and unique and exotic system we can find inside one of the most dense stellar systems that we know. And if this were to work, yes. So just to start, all stars in the galaxy and universe form in groups. These small groups, this can be small groups of a few hundred to maybe a few thousand stars, like here is the jewel box open cluster that are stars that form from the same material and forming this small group where you have around about 10,000 stars, or you can form these stars from a very massive cloud of material, and then end with a very massive cluster with millions or hundreds of thousands or millions of stars, like this one here that is M15, Messier 15. And you can see now the slight difference that in a scale that you have a few stars there in the center brightened in blue in this open cluster to this one that is basically completely crowded with stars. These systems with millions of stars are what we call globular clusters. And they are found in all galaxies. We look in particular to our Milky Way. This is a density map of all the stars that were observed with the satellite Gaia. It has been run by ESA for the last couple of years and then end this service just a few weeks ago, where basically every single point is an individual star that have been observed with this satellite. And some of these points there that you can see here, like this one, maybe this one, that bright one over there, all of these points are not stars, but are globular clusters. And in the Milky Way, we have around 150 well-known globular clusters, but the number is increasing over time. There are several candidate clusters, in particular in the center of the Milky Way, in the bulge, where it's harder to identify them, but the number can run from 150 to 200 or maybe more. Now, I was saying each of these points that I have marked here in white are indeed these massive groups of stars with a million of stars more or less each. So this small point here is that one, that is 47 Tucana, or the previous one that I showed in color that was M15 is this one. And these stellar systems are also very interesting for many things. My research is currently mainly focused on understanding how this cluster evolves and how the stars move inside. But just to summarize the main points that we can know from this cluster is that first, they are very old. Most of them have around 12, 13 gigayears. That is basically the age of the universe, which are also interesting to understand how the Milky Way was formed or how was the stellar composition very early in the universe. As I was saying, they have a lot of stars inside, between 100,000 to millions or multiple millions of stars. And the more interesting point for this talk is that they are very dense. So they are compact system. As you can see, you will see there was only a point in the image of the Milky Way, but you have millions of stars in this system. So just to put an idea of how dense these stellar systems are, here I have, well, the sun in the middle of this circle, and this circle basically denotes the volume from the sun to the nearest star. That is, in this case, is the triple system Alpha, Beta, and Proxima Centauri. And there are no more stars inside this volume because it's just the sun and the most closest star. Now, if we have 10 stars, we will do something like this. If we go in the same volume, we go to 1,000 stars, you're starting to see that it's becoming more crowded. And if we put 100,000 stars, you can see that's basically black. You cannot see any, it's completely full. And globular clusters basically have this density, are so dense that you have basically are packing like several 10,000 to 100,000 stars in just the volume given by the sun to the nearest star. So as you can imagine, when you are moving in a very crowded place, it's very hard to move because you have to move to the side to see the other person pass, dodge some other person moving behind you, and so on. People interact, and the stars will also interact with each other. This is a very simple video of a star moving, where basically they are feeling the effect of the nearby star, and then interacting with each other and moving in this kind of coordinated dance that is we will see in a globular cluster. I think that these have only 100 stars, so you can have to imagine this to the 10,000 times more stars in a real globular cluster. So because of these densities and this crowdedness, the star will, as I was saying, interact with each other. Now, if we're moving just to the next topics to try to find these very interesting treasures that are inside of globular clusters, I want to have a very brief review or summary of how stars evolve, just so because this is relevant for how the star will interact in the system. So if you look at a star and you look at how hot the star is and how bright the star is, as long as they have energy, so the gas tank is full, the star will be basically located at a given luminosity and a given temperature. And it will have a specific size. Everything in balance until the star runs out of fuel. When the star runs out of fuel, you will see that it becomes a little bit, the temperature will change, as well as the luminosity. And because of how the balance of forces in the star is working, this will go in a phase that is this line here, where the star becomes, it will inflate and become a giant. Now, if the stars have no more, doesn't have any other source of energy to keep running, it will stop there and it will become a white dwarf. That's something that it is. It will stop there, and it become a white dwarf. It is basically the nucleus of the star, where all the outer part of the star will just shed around, so it was all the gas that it was inside, and just have the very dense nucleus. Now, if the star half is more massive, it can become, instead of a white dwarf, it can go in explosion, supernova, and end with what we call a neutron star. That is the same original nucleus, but more dense, significantly more dense. This is basically, you will expect that these are composed by oxygen, carbon, very dense together. This one are composed of iron, much more smaller, dense, and tight. And in the most extreme cases, the star can become a black hole. Because it's so massive that will contract to the point that no light cannot go out and will become a very dense remnant, that is the black hole. Now, this happens if you only have one star, and it happens for all the stars depending on the mass. But stars also come in pairs. They are not alone, but they can come in two. And these are binary stars. And as you can imagine now, if one star moving around alone have to dodge and move around in a very crowded space, binaries also will have to move in this crowded space. And depending how the interactions with other stars goes, the binaries might either break, merge, or even change partners because of these interactions. For example, here I have a binary star system. We have two stars over here, and then a massive star, the number 3, that is on the other side. Now, this is a real simulation of just as a scale. This line here is the distance from the sun to Pluto. So we are talking on small scales at the level of stars. And if we start our simulation going, the binary will interact with this star, and then because they see each other gravitationally, they will start, bad idea to use it. Will start dancing around and changing from binary to triple system, maybe to a binary, and go on. This is something that happens in all star clusters for all the binaries that might have some kind of interaction of them. And if we keep going in this dance, seems that already there was an interchange, but nope, it went back and start to collide with each other. And almost, nope. And yeah, and we end with that, the smallest star, the number 2, going in completely wrong direction. And the 1 and 3 that were separate now are together as a new binary. So we have this also interactions where not only binaries can become tighter, disrupt, but also exchange. And we start with one configuration and we end with a completely different configuration. Now, if you put 2 stars in a binary system close enough, if one of them, as I was saying, inflates because it's losing the mass or was just more larger, we'll have the binaries starting is exchanging mass, interacting and exchanging mass. So usually the more massive one will start sucking out whatever is the gas that the more larger star companion has. And this change of mass is actually pretty interesting because it's basically what will create this unique system, these treasures that we want to understand and find in globular clusters. You can have a normal star with a giant or a more larger star. So the normal star is the one that is accreting. It will produce certain kind of object. You can have a neutron star that is much denser and star accreting mass will produce also a different kind of object that we will discuss. And finally, you can also have a black hole that will be accreting. Depending if the object that is accreting, either a star, a neutron star, or a black hole, we will have different outcomes and different exotic objects that we want to go. So let's start with the first one. That is indeed if you have only a normal star and a giant star. When you have this case, the normal star is taking mass from the massive one, and because of that, it can live for longer. I was showing you at the beginning, when the star run out of fuel, it will move to the right. So basically, once it runs out of fuel, it will move to this side. If you look at the temperature and the luminosity, the magnitude. But if the star is getting rejuvenated, it can live for longer. So it's not moving to the right, but it's moving up. And this is very unique of this dense system because all of them show these stars that are blue and moving away of the evolution track where the star is run out of fuel. And this extra fuel that the star is getting, why it's moving to the left side, is coming from these interactions. Either the star you can have two stars that at some point interact, collide, merge, and form a new younger, bluer star. Or you can have, I was indicating, a binary system to start moving together that at a given point start interchanging mass. So it's gaining more material and then becoming again a younger, bluer star. If now look at a different kind of the next step in our collection is when you have a massive a giant star and a neutron star. In these cases, neutron stars are basically really dense, extremely dense star and compact. For example, if you compact air to the side of a neutron star, it will be like at the size of a teaspoon. That's so dense they are. And one of these kinds of interactions that neutron star can have with the star is that they start spinning and moving faster and faster. This produces something that we call pulsars. These pulsars are basically lighthouses. You have a rotating neutron star that sends some beam of gas because of this accretion in one single direction, and we can see these pulses as a radio sources. And we have seen this also in globular clusters. 47 Tucana is the other big cluster that I showed at the beginning. And in that cluster, there have been several pulsars that have been found in the cluster that indicate this variability and pulsation as a lighthouse in the cluster. If we, and I didn't build up that one. And the last exotic object that I wanted to introduce you today was black holes. Now, if we have an object that is accreting mass from the nearby star, depending of the mass that the object has, it will bright hotter and hotter and hotter. In the case of black holes, they are so hot, they are so compact that the mass falling in the black hole brights in the X-rays. So there a lot of energy in the being emitted from this accretion disk. Now, for the longest time, because stars interact in cluster and how we expect black hole interacted in cluster, people thought that this black hole would just kick each other and should not be any black hole inside of globular cluster. But because of these accretion signatures, we have seen and observed signals that from this accreting disk in globular clusters that indicate the presence of black holes there. And since like more than 10 years ago, we are very certain that black holes can still survive inside of globular clusters. And these are the most extreme exotic objects that you can imagine. You also, if you have the chance of a few years ago, Interstellar, have this accreting black hole where they go across at the end of the movie. Now, we know that black holes not only might be in a binary with a giant star where they can consume mass, but black holes can be in a binary with another black hole. And this is so now we are starting to realize that these interactions where you have a binary that is very massive, like two black holes, they start to produce some kind of waves or ripples into space. And since almost 10 years ago, 2015, these ripples we are able to start measuring these ripples with very advanced observational systems here in Earth. And just to show you how these objects interact, so here in this video, you will see two black holes in the center that are moving around and producing these variations and changes in the space. You can see that the surface over here is a space. The black hole basically is kind of a hole in a space where everything falls. And as they move together, the forces become to produce significantly longer changes in the shape of the space. Now we are getting close to the merger. And once they merge, you will see that will be, yep, that is just when the merger is happening. And in the same way as if you go to a lake and throw a stone in the lake, you see there is formed some waves and ripples around. This merger will produce these ripples in space, which in practice, we can measure by things like basic extending or contracting a rule. For example, if we have this stick and we have a gravitational wave passing as the gravitational wave passing, the slit will elongate and contract. The changes of this contraction and expanding in a space are minimal to the size of basically of the size of an atom. And the only way to do it is with very precise lasers that have been built along kilometers long. There are two in the US, one in Italy. Now I think they're building one in India, and then there is some similar experiment trying to be built here also in Austria. Now, thanks for this kind of gravitational waves, now we can not only see the presence of these massive dark objects like black holes, but also interaction within neutron stars and so on. All these mergers that can happen when two binaries get too close together and bound in one single object. And since the beginning of these experiments, we have found several of them. And you can see that some black holes can form more massive ones when they merge. I think there is one neutron star that they also found that merge, two neutron stars that merge in a new object that produces a supernova. And if I remember correctly, this one was when they found that in this kind of explosions, when two neutron stars collide with each other, you will produce gold, platinum on all these very treasury metals. Now, this has happened not necessarily inside of cluster, but everywhere else, as long as you have two black holes that merge together. But in around 5 years ago, in 2019, one of these mergers of black holes produced an object that was 140 times the mass of the sun. And because of this, the constraint for this kind of mergers and signals is so well known, we can also estimate what was the mass of the two objects that merged together. And we have found that these are around 60 and 80 times the mass of the sun. However, we cannot produce black holes of these masses with the standard evolution that I showed at the beginning. You have a massive star, massive enough to produce a black hole of 60 or 80 solar masses. This star will explode and leave nothing before it can become a black hole. So there should not be these black holes just because of stellar evolution. But the question is where they come from. And one alternative is that these were also the result of two other black holes that merged before. So now we are observing kind of interactions in a binary black hole that merge that can be produced by the merger of previous two black hole binaries. So we have this kind of cascade hierarchical merger. And this kind of chain black hole mergers or interactions can only or mainly can be produced in places where you have many stars interacting each other, when there is a lot of interchange, a lot of binaries being built, binaries being destroyed, where you can put two black holes together and then the result put it together with another black hole just because they can interact. And this is again coming to the more precious kind of treasure we can currently trying to find inside of globular cluster. Yes, globular cluster being so dense are the most unique places we can try to find these objects. And with this in mind, I can just go to a summary of everything I have been saying today. Is that globular clusters are dense stellar systems, are compact and dense. So stars interact with each other. It's like moving in a crowded place. And this interaction can build binaries, destroy binaries, but also bring binaries closer together, which will trigger this massive change that can produce weird exotic objects like blue stragglers, so younger stars, or pulsars that are neutron stars that speed up because of a binary, or black holes and black hole mergers that can be produced by just the interaction of black holes inside of globular clusters. So at the end, we can say that while the small star clusters as the open ones can be a jewel box where you have a lot of gems writing, a globular cluster is indeed a treasure trove that not only you have the little gems writing, but you can find all these kind of unique and very exotic objects that can only be found there. And with that, many thanks for your attention. And I have there also to announce the next lecture or talk in this night of the STEM part. Thank you.
Thanks, Francisco. Are there any questions? Yep.
Yeah.
Is it in general or is it only in our galaxy?
So this indeed depends of galaxies. So our galaxy have around 150 to 100. There are massive galaxies like M87 that have like several thousands of globular clusters. So it's not the same number. Depends of the galaxy.
All right. Is it correct that these global clusters really counts to our galaxy?
Like they are bound to the galaxy. Yes, most of them are bound to the galaxy. So this is a very interesting point because now we are starting to think that some of these clusters might have been not originally from the Milky Way, but from galaxies that were accreted into the Milky Way. That are not the majority, but there are some of them that might have come along with the galaxy coming together. But most of them might have been from the Milky Way.
So if Earth was inside a globular cluster,
you mean if we were inside of a globular cluster, it will be completely different from what we see now? Yes. Basically, now we see several, if we were inside, there is a very nice image that now I think it would be nice if I had put it there, but you will see basically the night sky brightening with the stars, like almost like noon or evening, the same brightness of the sun, but just because of you have hundreds of stars. They probably might have no night because of how close the stars in cluster and how packed with the stars you will have the sky.